So hello students, in this video we are going to discuss about the use of two very important indicators, that is phenolphthalein and methyl orange, in neutralization titration. These two indicators are used simultaneously for analysis of a very common mixture, that is mixture of sodium carbonate and sodium bicarbonate. So let us start one by one the concepts involved in the uses of phenolphthalein and methyl orange indicators in acid-base titration. As we all know that most of the indicators used in acid-base titrations are they themselves either weak organic acids or weak organic base, and indicators have characteristic color at a specific pH. That is, before that pH, indicator has one color, after that pH, indicator has another color, and at end point, indicator changes from one color to another color because at end point there occur a sudden change in pH of the solution. So that pH must match with the pH range of indicator that we discuss in ionic equilibrium. Here we will just be concentrating on the role of these two indicators, how these indicators are used in analysis of acids and bases. So first of all, let us know something about phenolphthalein and methyl orange. Phenolphthalein let us indicate it by pH H, where H indicates the acidic hydrogen. This acidic form of phenolphthalein is colorless. However, its conjugate base is pink colored. Obviously, if the solution is acidic, then due to common ion effect, this form will predominate. If the solution is basic, this conjugate base will predominate. At a specific pH, phenolphthalein changes from one form to another form. Approximately at pH 10, this change is observed. That means if pH is greater than 10, if pH is greater than 10, means solution is strongly basic. The solution will have pink color. But if pH is less than 10, although solution is basic, but phenolphthalein exists predominantly in unionized form and solution remains colorless. So we can say that at pH above 10, phenolphthalein will have pink color, and at pH below 10, phenolphthalein will have no color, colorless. So 10 is the transition pH for this phenolphthalein indicator. Similarly, there is another indicator called methyl orange. Let us indicate it by this notation. This acid form of methyl orange is yellow colored. Sorry, acid form is orange color. Acid form of methyl orange is orange colored, and when it ionizes, its conjugate base is yellow colored. And this methyl orange changes its color at about pH 5. So if pH is greater than 5, the solution will be yellow color, and if pH is less than 5, the solution will be orange color. So they are the basic facts about the color of phenolphthalein and methyl orange. Now, how these two indicators are used in acid-base titration, let us see that. Suppose we have a mixture. Suppose we have a mixture of sodium carbonate and sodium bicarbonate. Both of these salts are basic in nature since they are salts of weak acid, carbonic acid, and strong base, sodium hydroxide. So both are basic in nature. Sodium carbonate is more basic than sodium bicarbonate. Both have their pH greater than 7 in aqueous solution. When these two are combined in solution, the pH of solution lies at around 12 or even greater than 12. We can say that lies between 12 and 13. So if we add, say, 1 drop of phenolphthalein, the solution will develop pink color since at pH greater than 10 the solution will show pink color. Now if we titrate the solution, by adding some strong acid, say HCl is being added, what will happen? The strong base sodium bicarbonate will start neutralizing. Sodium bicarbonate will start neutralizing. Okay. So if we add HCl, the stronger base sodium carbonate will start neutralizing. So what will happen? Sodium bicarbonate Na2CO3 will start neutralizing first to sodium bicarbonate NaHCO3 like this. Since sodium carbonate is a stronger base, it will be neutralized first, and neutralization occurs in steps. So sodium carbonate will first be neutralized into sodium bicarbonate, and then bicarbonate will neutralize further once the sodium carbonate is neutralized completely. As this titration proceeds, the stronger base will be consumed from the solution and pH of the solution will decrease gradually. The instant at which sodium carbonate is completely converted into sodium bicarbonate, the pH of the solution comes out to be less than 10. pH of the solution comes out to be less than 10 and the solution becomes colorless. So we can say that to reach the phenolphthalein end point, the moles of HCl, moles of H plus required will be equal to moles of sodium carbonate present. Since 1:1, stoichiometry is there, 1 mole of H plus is neutralizing 1 mole of sodium carbonate into sodium bicarbonate. So moles of H plus required to reach the phenolphthalein endpoint will be equal to moles of sodium carbonate. So we can say that moles of H plus, be very careful in this titration, always carry out the calculation using moles of H plus rather moles of acid. That may create confusion if you have sulfuric acid or acid like that. So moles of H plus is equal to moles of sodium carbonate to reach the phenolphthalein endpoint. Correct? Now, suppose we have added methyl orange indicator, not the phenolphthalein indicator. Then what will happen? Now, we have mixture of sodium carbonate and sodium bicarbonate in solution, and as we have already said that pH will be greater than 12. Now add some 1 drop of methyl orange. What will happen? The entire solution will become yellow. The entire solution will become yellow since it is strongly basic. Now start adding acid in the same manner. Start adding hydrochloric acid. Now what will happen? Once again sodium carbonate will be neutralized first into sodium bicarbonate. So sodium carbonate Na2CO3 will first neutralize into sodium bicarbonate NaHCO3 and Na plus. The instant at which the entire carbonate is converted into sodium bicarbonate, the pH is still greater than 7. It is 10, around 10, we have already stated here. So pH is greater than 7. So methyl orange will not change its color at this point since methyl orange maintain yellow color up to pH 5. So solution will still remain yellow. We won't observe anything visually. So what we'll do? We'll continue adding acid. In the next step, the sodium bicarbonate. And now the sodium bicarbonate in solution is from the two sources. One is from original. We had sodium bicarbonate originally in the solution here, and some sodium bicarbonate produced in the first step of titration of sodium carbonate. So original plus from Na2CO3. Now if we add H plus further, what will happen? It will be neutralized further into Na plus and H2CO3. At the end of this titration, there will be no basic component in the solution. All carbonates and bicarbonates are now neutralized, and the solution has dissolved carbon dioxide, which gives solution acidic nature, and the pH of solution comes out to be less than 5, and solution develop what? Orange color. So when the solution changes from yellow to orange, it indicates that the entire carbonate as well as the original bicarbonate are now neutralized. So once again, phenolphthalein endpoint indicates that the entire sodium carbonate is converted to just sodium bicarbonate. But methyl orange endpoint indicates that sodium carbonate is first converted to sodium bicarbonate and then the entire sodium bicarbonate from original sample and the one produced from sodium carbonate are neutralized to carbon dioxide. Then color change of methyl orange will be observed. So now let us take this qualitatively, so quantitatively how it is done. Suppose we have a solution which contains say x millimole of sodium carbonate and y millimole of sodium bicarbonate. If we carry out titration into different sets, once using methyl orange, once using phenolphthalein, and then in a second set of titration, second experiment using methyl orange, then the calculation will be done in this manner. So titration 1, let us call it titration 1. Phenolphthalein is added. Now what will happen? Na2CO3 will be neutralized to NaHCO3 and Na plus. So since we have x millimole of this, x millimole of acid will be required to reach this end point, and here at this point solution will turn from pink to colorless. So what we'll have to do? We'll have to just calculate the millimoles of H plus added to reach the end point where solution has turned from pink to colorless. And we say that millimole of sodium carbonate Na2CO3, which is equal to X, is equal to millimole of H plus is added. Millimole of H plus added. Then we carry out a second titration, titration 2. Now we'll take the same volume of the sample solution and now methyl orange is added. The result will be, solution will be yellow since it is strongly basic. Now start adding H plus. What will happen? Na2CO3 will first be neutralized to NaHCO3 and Na plus. Since there is X millimole of sodium carbonate, for this step X millimole of H plus will be required and X millimole of sodium bicarbonate will be produced. But since pH is around 10, the solution is still yellow. Next, since we don't observe any color change, we'll continue adding H plus. In the next step, what will happen? NaHCO3 will be neutralized by H plus, but now the millimole of sodium bicarbonate will be X plus y, x from the first step of reaction and y original, since we have assumed that there is y millimole of sodium bicarbonate. So now for x plus y millimole of sodium bicarbonate, which will be neutralized like this, x plus y millimole of H plus would be required, and now the solution has pH less than 5, it will become orange color. So in order to reach from yellow to orange, the millimoles of H plus required is 2x plus y. X here, x plus y here. 2x plus y is equal to millimole of H plus required to reach the methyl orange endpoint. So from phenolphthalein titration, we have already determined x. Now from the second titration, we know 2x plus y, so substituting x from the first experiment, we can determine y, and we can know the amount of sodium carbonate, sodium bicarbonate in the sample. This is one way. This can also be, this titration, this experiment can also be done in a different manner. Let us call them titration 2. Second type of titration. In this approach, we first add phenolphthalein. We determine the phenolphthalein endpoint, and then we add methyl orange at that point. So once again we have sodium carbonate x millimole and sodium bicarbonate y millimole. Now add phenolphthalein. Solution will become pink. Now start adding acid. What will happen? Sodium carbonate will be neutralized only in the first step to sodium bicarbonate, NaHCO3 and Na plus. The moment this reaction is complete, the solution will become colorless. So X is equal to millimole of H plus required to reach the phenolphthalein endpoint. Now rather performing second set of experiment, what we do here, the solution has become colorless. So what we are going to do, we are going to add methyl orange at this point to the same solution. Add methyl orange. Since pH of solution is still much greater than 5, it is about 10. So the moment we add methyl orange, the solution will become yellow. Now start adding acid. What will happen? Sodium bicarbonate, NaHCO3, will now start neutralizing to give carbonic acid. And the moment this step is complete, the solution will become orange, from yellow to orange. But in this step, the millimoles of sodium bicarbonate being titrated is equal to X plus Y. X produced from sodium carbonate and Y original. So the millimoles of H plus required will be X plus Y. So now X plus Y is known, X plus Y is known, and X is known from the first experiment. Substituting X in X plus Y, we can know the value of Y, and so analysis can be done in this manner. So that is how phenolphthalein and methyl orange is used in acid-base titration. Now it would be better if we apply them in solving some of the numerical questions usually asked in IIT JEE. So let us start working on the role of these two indicators through problems. So let us start with a simple problem. Problem number 1. Determine mass percentage of sodium carbonate and sodium bicarbonate in the sample. Now this question is regarding analysis of a sample containing sodium carbonate, sodium bicarbonate. So let us assume that 10 ml of the solution has, say, X millimole sodium carbonate and Y millimole sodium bicarbonate. Y millimole sodium bicarbonate. In experiment number 1, when phenolphthalein is used, only sodium carbonate will be neutralized to sodium bicarbonate. So only reaction will be Na2CO3 plus H plus giving Na plus NaHCO3. So X of this will require X of this, which is equal to 16 ml 0.1 molar sulfuric acid. So 1.6, 16 into 0.1 into 2, we are calculating millimole of H plus sulfuric acid is dibasic acid. So millimole of H plus will be 2 times millimole of sulfuric acid. So it is 3.2 millimole. In the second experiment, what will happen? In second experiment, first Na2CO3 will be neutralized to NaHCO3, and for X of H plus would be required and X of sodium bicarbonate will be produced. In the next step, we have NaHCO3 X plus Y millimole, X here and Y original, plus H plus, giving Na plus H2O CO2, and here again X plus Y millimole of H plus would be required. So total hydrogen ion required is now 2X plus Y, which is given 2X plus Y is equal to given 40 ml, see here, 40 ml 0.1 molar, so 4 millimole. So x plus y is 4 into 2, 4 millimole of sulfuric acid. So 8 millimole of hydrogen ion. So 8. X is known, it is 3.2. So y will be equal to 8 minus 2 into x, which is 3.2. So 3.2 into 2, 6.4. 8 minus 6.4, 1.6 millimole. Analysis is done. Now we know millimole of sodium carbonate. We know millimole of sodium bicarbonate in 10 ml. So now it is just simple calculation. So total millimole of sodium carbonate Na2CO3 will be equal to how much? 5 times. We have calculated in 10 ml, so it will be 3.2, sorry, 3.2 into 5. Yeah, 3.2 into 5. So it is 3.2 into 5. So it is 16 millimole. 16 millimole, and if we calculate it into mass, it will be 16 into 106 upon 1000. 106 is the molar mass, so it will be 1.696. 1.696 gram. So it will be 1.696 upon 2.5 into 100, which comes out to be 67.84%. Similarly, total millimole of NaHCO3 will be 1.6 into 5, 1.6 in 10 ml, so into 5 into 50 in 50 ml. So it is 8 millimole. So it is 8 into 84 upon 1000 grams. So it will be 0.672 gram. 0.672 gram. So 0.672 upon 2.5 into 100. So it will be 26.88%. So that is how we carry out the calculation based on the experiment involving uses of phenolphthalein and methyl orange endpoint. Let us work out one more problem. The question is now the question is 3 gram determine mass percentage of NaOH and Na2CO3 in the sample. Now in this problem, rather sodium bicarbonate, we have sodium hydroxide and sodium carbonate mixture. Now sodium hydroxide is further a stronger base than sodium carbonate. So now when titration is carried out, first sodium hydroxide will be neutralized to NaClH2O. Then sodium carbonate will start neutralizing. But once sodium hydroxide is neutralized, sodium carbonate is still there in the solution. So pH of the solution will still be greater than 10, and if phenolphthalein is there, the solution will be pink color. So no color change will be observed. Now if acid is added further, sodium carbonate will start converting into sodium bicarbonate, and the point at which sodium carbonate is converted completely into sodium bicarbonate, then only the solution will become colorless. So now the phenolphthalein endpoint will be reached only when NaOH is completely neutralized and sodium carbonate is completely converted into sodium bicarbonate. In presence of methyl orange, endpoint will be observed when the neutralization is complete. That is, the bicarbonate is further neutralized into carbon dioxide and water. So once again, what we are going to do, let us assume, let 10 ml sample solution contain X millimole NaOH and Y millimole sodium carbonate. In presence of phenolphthalein, the reactions involved are NaOH will be neutralized first into NaCl H2O and then Na2CO3 will be neutralized to NaCl NaHCO3. So for X millimole of sodium hydroxide, X millimole of HCl would be required. For Y millimole of sodium carbonate, Y millimole of HCl would be required. So now X plus Y is equal to how much? Millimoles of HCl. 40 into 0.1, so 4. So it is 4. In presence of methyl orange, what would happen? NaOH would be neutralized completely to NaCl and H2O and Na2CO3, sorry, it is HCl, sodium carbonate would also be neutralized to 2NaCl plus H2O plus CO2. So for X millimole of H plus, for Y 2Y millimole of HCl. So now X plus 2Y will be equal to how much? It is 5.5, 55 ml, 0.1 molar, so 5.5. And first equation was X plus Y 4. So if we solve this to Y is equal to 1.5, X is equal to 2.5. Correct? Yeah, 2.5. It is the millimole of sodium carbonate. It is the millimole of sodium hydroxide. So again, X is sodium hydroxide. Yeah. So mass of NaOH would be equal to its mole 2.5 upon 1000. Millimole is now converted to mole into 10. So this is the millimole in 10 ml only. So in 100 ml it will be 10 times into 40. So it is 1 gram. So it will be 1 by 3 into 100, 33.33%. Similarly, mass of sodium carbonate, that will be equal to 1.5 into 10 for 100 ml upon 1000 into 106. So it is 1.59 gram. So it will be equal to 1.59 upon 3 into 100. It is 53%. So that is how calculation is done. So let us work out one more problem on this. This is a bit exhaustive problem. So let us try to understand. The question is, deduce formula of acid assuming that it contains only carbon, hydrogen and oxygen. It's a bigger problem. From the first information, 0.1 gram of acid required 8 ml, 0.1 molar NaOH, we can determine the molar mass of acid. So let us start from there. Acid is monobasic, so 1 mole of acid would require 1 mole of NaOH. So millimole of NaOH required is 8 into 0.1, 0.8. So 0.8 millimole will neutralize 0.8 millimole, which is also equal to 0.1 gram. So now we can calculate 0.8 millimole RCOOH is equal to 0.1 gram. So 1000 millimole, which is 1 mole, will be equal to 0.1 upon 0.8 to 1000, which is equal to 125 gram, and this will be the molar mass. Molar mass, since it is mass of 1 mole 1000 millimole. So now we know the molar mass. The next is titration of solution containing sodium carbonate and sodium hydroxide. How we come to know that the solution through which CO2 is passed contains sodium carbonate and sodium hydroxide? It is given in the question that CO2 is passed through excess of NaOH solution. So CO2 will be neutralized completely to sodium carbonate and some sodium hydroxide will be left unreacted. So now let us assume that half solution has X millimole Na2CO3 and Y millimole NaOH. So now X is equal to phenolphthalein endpoint gives the millimole of sodium carbonate. So S is equal to millimole of H plus required to reach the phenolphthalein. Sorry. Now NaOH is also neutralizing. So in the first step, X plus Y for NaOH, X for sodium carbonate to reach the phenolphthalein endpoint is equal to 20. When methyl orange is present, sodium carbonate will be first neutralized to sodium bicarbonate, which will be neutralized further. So for X millimole of sodium carbonate, 2x millimole of acid will be required. So 2x plus Y, that is equal to 34. So solving this two, X is equal to 14. 14 and Y is equal to 6. We are interested in X. It is the millimole of sodium carbonate. And since sodium carbonate contain one carbon, so we can say that 1 mole of CO2 will give 1 mole of sodium carbonate. So this is also equal to millimole of CO2 in half solution. It was separated into two halves. So now we can say that total millimole of CO2 produced is equal to 2 times this. So 14 into 2, 28. 28. Now let us assume the formula CXHYCOOH. This is the formula of carboxylic acid. Upon oxidation, it will produce X mole of CO2. X we have already taken no matter. X mole of CO2, sorry, X plus 1, not X. X plus 1. Here we have X and 1 here. So X plus 1 mole of CO2. And 0.5 gram of this is taken. Correct? So 0.5 gram of this, 0.5 gram of this means 0.5 upon 125 mole, and 1 mole of this gives X plus 1 mole of CO2. So this much mole will give 0.5 upon 125 into X plus 1, and that is equal to 28 millimole, so 28 upon 1000 mole. So if we work out, it is 4 7 ja, sorry, it is 8. So 8, yeah, 8. So 5 into 8, 0.5 into 8 will be 4. So it will be, just 1 second, what we have here. So 0.5 upon 125 into X plus 1 is equal to 28 upon 1000. So 125, 8 is a 1000. So 8 into 0.54, 28, 7. So X plus 1 is 7, X plus 1 is 7, so X is 6. So X is now known, X is 6. Then how to find out Y? Y can also be known, since we have 0.5 gram. So molar mass of this is known, so just calculate the molar mass. So molar mass of this will be 12 into 6, already we know X, 12 into 6 plus Y into 1 plus 45 for COH whole, and that is equal to 125. So if we work out, it will be equal to, Y will be equal to 9. Sorry, not 9, it will be 8. So in this manner, the formula we have derived is C6H8COOH. This is the formula of this